Okay, I believe we're live. Hello, everyone. Thank you for joining us today. I'm sure there's some recognizable names in the attendees list, and if we know each other already, you're watching this afterwards, after the event, a warm welcome to you. So today we've got a webinar on some typical problems in Cassandra that many of you have faced before. And I've got two of my favorite colleagues joining me today, Francesco and Romain, who are both from support, but they've been around for a long time, and I've worked with them on a number of tickets with customers and always been thoroughly surprised, inspired. They've taught me some things along the way. When I was asked a couple of weeks ago, or maybe a month ago now, if I could do a webinar, my first thought was, hey, let's get together these two people and let's talk about problems. Knowing that this type of information is highly valuable for all of you. Some of the stuff that we'll be talking about today is problems with partitions, problems with repairs, how to set up disks, the choice between JBODs and LVMs, how to do upgrades well, how to set up your system or the Linux distribution properly, and different tooling and operational methodologies. Also, a quick touch onto what's coming in Cassandra, both what's exciting, will open up new use cases for you, but also what can help make life easier as an operator for you. And one of those things will be vector search. This is very hot at the moment, so we wouldn't do it justice if we didn't touch on that lightly. And at the end, there'll be an ask us anything section. Before we jump into that, we've got a couple of introduction slides to go through. So first off, a bit more of an introduction of the three of us. I can go first. So I've been involved in Cassandra going back to 2011. I wasn't interested in databases before Cassandra. Cassandra was a technology that came along, and in the way that it solved distributed problems, it felt more akin to how we were solving problems in a distributed space everywhere else in our industry. That opened up a lot of doors for me, and the rest was history. Since then, I've become a Cassandra committer, and I'm now on the PMC. And I've had many roles, both as consultant in services, as an engineer, and in product. I'm back as an engineer now, helping build the DSC and HCD products, and thoroughly enjoying it. A little bit personal about myself. I am an Australian. I met a Norwegian wife along the way, moved to Norway on and off, have been living in Norway for 20 years. And one of the real blessings in life is the opportunity to live in Europe. I absolutely love working with the diversity that's available here. And I'm hoping that Romain and Francesco can also share a little bit about their backgrounds and what they bring to the table, because I think working in teams, working with different cultures, it is for me one of the joys in life. Francesco, would you like to go next?
Yes. Hi everybody. My name is Francesco Animali. I'm Italian. I currently live in Italy. I've been living in UK for about 15 years, up to 2020. I have known databases from a long time, and I've been working on pretty much all the database types, starting from MySQL, Postgres, and Oracle, DB2 a lot for many years. Then in 2016, I I fell in love with Cassandra, and in particular with the distributed databases, that the technology that is behind that it really opened my eyes, and because it's such a difference. There's such a dramatic difference between the relational databases and non-relational distributed database like Cassandra. So I love Cassandra. I've been working with Cassandra for the past 8 years plus, enjoying the technical side of it, enjoying working with customers or with many different projects, use cases. It really never stops surprising and never stops interesting and teasing my brain. Everything we do in support is about learning yet a new thing. It seems kind of weird, but in 8 years, I can say that I pretty much learned something every day from my colleagues, from my customers, from the engineering team, anything. So that's the very interesting part of my job in support. It is also always you need to work in teams, you need to work in a group, you need to exchange constantly your ideas with ideas of others. So yeah, I hope that we will bring some nice discussion about Cassandra things. So I'm really looking forward to hearing questions from you.
And I couldn't agree with you more, Francesco. I think it's learning new things every day. It's a technology that you don't hit the bottom. You always can keep digging and learn new stuff. And having a good group of people around you to spar with is a wonderful thing for us. Romain.
Hello, everyone. My name is Romain. I'm French. I've been living in the UK for 18 years now. Been in the IT industry for a bit longer than that. Worked for 11 years in the business analytics area, business intelligence, more exactly. And I joined the DataStax and Cassandra community in 2018. So it's been 6 years and a half I've been working on the technology. Bouncing on what Francesco and Mick said, I remember when I first started to learn about Cassandra, that I found it interesting to have to ditch all my existing concepts about RDBMS to actually work on a NoSQL database. I remember this vividly shocked me at first.
Yeah.
Fun fact about me, I used to do cliff diving, but I got wiser over the years, and I don't think I'm at an age where I should be jumping or backflipping from 10 meters high cliff.
Oh, wow. Yeah, that sounds awesome. Keep going. Yeah, that sounds awesome. We'll do it together one day. How's that? I'll get you back into it.
Anytime.
Okay. So before we keep going, some house rules for us. Through the presentations, there's going to be some links that pop up. These are call to actions or further reading on some of the things that we are talking about. So if you see them pop up, we recommend that you click on them, save them, read them later. We've carefully selected them for you. This whole webinar, it's going to be recorded, so and emails will be sent out afterwards, so you can watch it again. You can pass it to your friends and colleagues, etc. In the SQL app, this webinar page, we do have a few tabs on the right-hand side. We've got chat and we've got Q&A. If you've got questions, throw them into Q&A. We're going to hold some time off at the end and answer all your questions. If there is something which is pertinent in the moment, feel free to also write something in the chat. We'll pick up on that as we go. Okay, so jumping into the content, this is how we're going to lay it out. We're going to go through some of these hot topics for operators first, and then wrap up with what's coming and what's hot in the use case and the development. So first up, we've got hot and wide and large partitions. I think we've all done a lot of time on this one, haven't we? So before I jump into this, Romain, I'm going to ask you an initial question. People will often just talk about large partitions, and when we were discussing this before, we laid this out between hot partitions and wide partitions and large partitions. Do you want to quickly give us the difference between them?
So let's start first with what is a hot partition. The way Cassandra is designed is to allow you to do a replication factor of 3 for your data, and your driver will come with an agreement as to the consistency level it needs to reach to receive its response from the database. So in a local quorum scenario, you will ask 2 of the nodes to retrieve the data. Now, a hot partition is basically when you're always hitting the same partition, hence the name. And that means that in the way Cassandra is designed, you will always be hitting the same nodes. So a hot partition is something that, however you scale your cluster, will never be sorted by any scaling, because the way you request a partition key will hit a specific token, and that token is always on the same 3 nodes. So that's what defines a hot partition. And so it doesn't matter if you have 3 nodes, 10 nodes, 100 nodes, 300 nodes or more. Hot partition will always give you that problem of creating a funnel to a specific set of your environment. Wide partitions is different in that it's the way you create your data in your partition key. And so if you create a partition key, or a primary key, which contains, let's say, 1 column as the partition key and 1 column as the clustering column, you can have multiple rows coming in your environment, coming in that partition. And the problem you get is when the number of rows within a partition get out of control, which means we say from a conservative perspective that a partition should avoid being above 100 meg. So from a support perspective, we know it's a conservative value, but that's because we know that when you start to see this, you will end up potentially seeing these particular partitions grow bigger and bigger. And the challenges around the wide partitions is that they will create pressure on your system. If they grow totally out of control, they will OOM your system. And so that's the definition of the hot and the wide partition. Hot partition is always hitting the same node. Wide partitions will also give pressure on some systems, but in a different manner. One is just constantly asking the same data to the same node, and the other is due to the bloating of the amount of data you request from the nodes.
And large partitions, which can also be large rows,
Yeah.
they're in fact something different.
So a large row is when you try to push too much data within one specific row. So typically using blobs and trying to push a full document within when you try to push a full document, a full binary within the database. So that's again something different. We do see one of the red flags for this is when you start to see the commit log segment size increased in the environment. This is not the only giveaway, but that's generally a good indication that you're trying to push too much within the rows of your database. The issue is that. Go ahead, Francesco.
There are also some alerts in Cassandra, right, that prevent you to, like you said, the commit log. When Cassandra detects that you are pushing a mutation that is more than half the size of the commit log, it will stop you, right?
Yeah, a write which is half the size of a commit log segment size will be refused by the database. So that's why I say the commit log segment size is one example where this can be some form of red flag. There's another thing to take.
That's why you should increase the size of the commit logs.
Well, no.
No,
you should reduce the size.
You
should reduce the size of your row.
I'm tricking you. I'm tricking you.
Yes.
No, of course not. Yes.
So the problem associated to the large rows and partition actually is inherent to the JVM. Your young generation is actually split in regions. 1024 to 2048 of them. And the problem you have is that when you're querying that data, you generate what you call an Among Us allocation, which means that this data does not go through your young generation and will actually go straight in the old gen of the JVM. Okay. And by doing that, what this creates, if you have a lot of large rows, it means that your cluster is going to start doing stop the world's GCs, what we call full GCs. And that really becomes a problem in your environment. The advice for this being to actually take the documents and store them outside of the database in that case, or to store your blob within a storage that you link within the repository you have in your Cassandra environment.
And there are some settings that can help protect against this now in newer versions. You can set the max cell size. There's a few things you can do, isn't there?
Yeah, the guardrails which have been implemented. Is that what you're referring to, Mick?
Yeah.
Yeah.
So going back to hot partitions, you did kind of mention that. What's some typical ways that this is obvious? Like when support tickets come in and the operators are like, my cluster keeps on falling over, I don't know what it is, and you see something and you're like, I know exactly what it is.
So I kind of gave the hint by explaining the way this reflects. So because you're always pinning your workload on the same nodes, those nodes will have a totally different CPU usage compared to the others. In general, if 90% of your traffic is hitting the same partition, those nodes are going to exhibit a way higher CPU level. So what you will find in that case is 3 nodes, or depending on your replication factor and your consistency level, those nodes will actually be a lot hotter in terms of CPU usage. And And one way to look into it further is, for example, using the node tool top partitions tool, which is not one we use on a daily basis. But when you start seeing that kind of significant CPU workload difference between your environment, that's generally a good one to start looking at, to sample your environment and find a bit the structure of the reads and the writes on specific tables.
Okay, and my last question before we jump on to the next slide is wide partitions. This one can be a little bit more tricky sometimes because sometimes you have for example, time series data models, like the idea of having 1 million rows in a partition, sometimes that is legitimate. So sometimes it can be a initially poorly designed data model, or it may have been a data model that was originally correct, and then a change has happened along the way, and that breaks it. What are the ways that you see it, and what are the ways that we can fix it?
So one of the thing that's noted here is that we have a tool such as Node-Tool CFStats would allow you to see potentially the largest partition in your environment. However, this can be misleading. I've recently encountered that where looking into a heap dump, I realized that I had a specific partition being called, which was more than 4 gig in memory. It was a small Cassandra cluster. There was not a lot of heap allocated to it. And that 4 gig query and the environment. And when I read in the heap dump, realized that it's a single partition rate. So I'm not talking about a range query or anything. It was really a single one. However, when I looked into the CF stats, I realized that you have only 1 gig shown here. So I think one of the key takeaway I want to give here is that the CF stats give you only the largest partition within an SS table across all the SS tables. It doesn't give you this across all the different SS tables. So there's no aggregation of the SS table metadata in the CF stats showing you that. So what you have to understand is that when we tell you we see a 100 meg partition, if that partition exists across multiple SS tables in your environment, it can be actually quite significantly bigger. A way to identify this is looking into the logs. If you see the white partitions are notified, and depending on the versions you use, some of them will actually even tell you which partition key within a table is actually giving you trouble. This is not always working because I just mentioned that the partition can be spread across multiple SS tables. So in a time series, this wouldn't occur. But in STCS or in STCS, you could end up with that. LCS, you would obviously see it based on the way LCS is designed. On compaction, it should really flag it up.
I'm going to jump on. I'm going to move on just with an eye on time. But I do want to say that both that caveat with the CF stats, that was something that you taught me. When you mentioned it, I was like, really? And I thought about it. I'm like, yeah, from code, that makes sense. And that's kind of embarrassing. Why haven't we fixed that yet? But that's the way things are. So thank you.
I had the same. I had the same as you when I was looking at that heap dump with 4 gig of data on a single rig partition, and I was looking at my CF stat on the other side, and I had only 1 gig showing in the CF stat. I did have to go and dig and discuss around to understand where that was coming from. So yeah, it came to a surprise as it came to me.
One of those little hidden gems. Okay, moving on to repairs. Francesco, you're our expert here. Do you want to tell me about the problems that we hit with large partitions, with tombstones, with V nodes, with tables, with dense nodes? That first line. You can introduce repairs too, but I think we can jump into it.
Yes, you can go on. So repair is an amazing background service. But it's a misnomer because it shouldn't be called repair, because repair gives a wrong idea about what it is. It's not repairing anything. It's ensuring that data is consistent in a distributed environment like Cassandra, Capsphere, and all the rest. We are trading immediate consistency for speed and availability. So in Cassandra, we want the database to be extremely fast, and we've got some amazing examples or very recent examples of our customers using big Cassandra cluster reaching levels of 4 million requests per second, 4.5 million requests per second consistently. So Cassandra is super fast. When it comes to speed, it's super fast. When it comes to availability, it is available, always available. But when it comes to consistency, it will not be immediately consistent. So that's what repair is. Repair is a background process that will ensure consistency. What it does is it will go partition by partition, node by node, and will add the nodes. What's your version of this piece of data? What's your version? And then it will put them together and stream and compare the data, one node and the other nodes and all the three replicas, and then stream the data across. So now it's a crucial service, but it does a lot of work and it's got some impact. And it is very sensitive.
Yeah, we often see customers. We often see customers either not doing repairs at all, or they come in and they do repairs. They don't quite understand the nuances, what the mechanism is really about, and so they're just trying to repair everything in a kind of without tuning it, and they can't get the repairs done in a way. It's exactly what you say. It's a heavy background process.
That's true. We've seen everything in support about repair, and repair has been there since the beginning of Cassandra. So, and in a way, it hasn't evolved a lot in the past up until version 4. In version 4, there are clear improvements. We will talk about them later. So repair is very sensitive to different things. It's very sensitive to the amount of vnodes you're using, the amount of the large partitions that we were talking about before. It's very sensitive to the total amount of data in the cluster, on the nodes. So the old, what they were called anti-patterns, Cassandra anti-patterns, they are very significant. They are very impactful for repair. And repair needs to run quickly, it needs to be consistent, it needs to be predictable. So it's very important, because otherwise there are other issues in the data. So the data will not be consistent eventually. So if repair needs to be guaranteed a nice and easy life, but there are many different things that, so vnodes, a Cassandra cluster with a high number of vnodes will make sub-range repair generate an amazing amount of tasks and sub-ranges that eventually it can become a problem. Large partitions, tombstones are all kind of roadblocks for repair, because they fall in the read path, and repair also uses the read path. So reading a very large partition with a lot of data in that partition, it will slow down repair. Tombstones will slow down repair. A lot of data will make repair go above, again, slow down repair and go above the threshold of the very famous, very important GC grace period, GC grace second. So repair is a very tricky service, very crucial, and the user needs to monitor that, needs to ensure that repair has got an easy life within the time of GC grace seconds. So
with what changed in Cassandra 4? There's a few things that changed in Cassandra 4, and we're seeing people kind of having to learn new things and trip up on newer versions of Cassandra.
Yes, Cassandra 4 brings back an old kind of an old project, but an old repair. Repair was born to repair the entire amount of data in the cluster, and initially in version 2 and version 3, incremental repair was brought in, and it was set as default as well. Now, incremental repair as opposed to range or sub-range repair will mark SS tables, will mark partitions as repaired, SS tables are as repaired. So when you run incremental repair, it will break down the SS tables, will anti-compact the SS tables, repair a number of partitions and a number of ranges, and create two different SS tables, one with repaired data and one with unrepaired data, and mark the repaired data with a repaired at property in the SS table.
Yeah.
So the idea is good.
Yeah, I mean, I think one of the challenges that people have with it is, you now have these two, what you said, you have these two sets of SS tables now from through the lens of repair, an unrepaired and a repaired. And so what repairs are actually doing is they're doing twice as much work. And there can be a amplification that's happening there. But the incremental approach means that you can kind of just do the deltas. So the idea is that you, even if the cost is double, you're chunking it down into smaller sizes and not having to worry about older stuff. The idea works well. It doesn't always work in practice. It depends on a few things. So understanding that is important. Francesco,
if I may, in an ideal world, you wouldn't need repair. But the way Cassandra works is try to give you just high availability, and by doing so, will sometimes allow a write to not make it to, let's say, the third node in your environment because you've requested a write at local quorum. It would normally do this. So the three nodes would receive the writes, even if you request a local quorum. So in an ideal world, if your cluster is always healthy, there will not be a need to run a repair. But the issue is, it will happen at one point or another that there's, for a reason, a system that goes down, some nodes which are actually not responding in time, because we mentioned some scenarios where this can happen. And when that happens, you want to make sure the data gets resynchronized across the board. And that's where, so I am with Fraser that it should be called resynchronization rather than repair.
It's to help with the read latency, because normally you want to you enforce consistency at request level anyway. So it could be write level consistency or read level consistency. So the data should be fairly consistent already. But this depends really on the type of the use case for very fast writes, very fast reads. I mean, repair is always there for ensuring a consistency in the end. But yes, like you were saying, Mick, incremental repair was a great invention because it allows to do repair only deltas or increments. But yes, the implementation then didn't provide the expected performance, in particular because with there's a risk of some SS tables not being included into the repair if they happen if the streaming happens after the Merkle tree has been built. So there are some edge cases, some scenarios where you can, in fact, remain with some data that is not completely repaired. The version 4, Cassandra 4, has completely reworked the incremental repair
and fixed a lot of those bugs. Yes,
and fixed a lot of bugs and changed the way the Merkle tree and the time the Merkle tree is created. In this way, because the anti-compaction was also a major overhead for incremental repair, compacting and anti-compacting all the time. And for slow systems with slow disks, that would already be impactful. So in this way, anti-compaction in Cassandra 4, anti-compaction is done before the Merkle tree is created. So in this way, the Merkle tree will contain the data from all the SS tables that are not repaired. And then the Merkle tree is exchanged and compared amongst nodes, and eventually the streaming happens. So Cassandra 4 brings back incremental repair. It's the default, and it has completely changed with respect to version 3. So it's probably the best way to do repair now. And also the entire, just to finish, the entire repair task. So each repair task is enclosed, is wrapped into a Paxos transaction. Paxos also has been completely reworked in version 4. We're not going to talk about that because it's a big thing. But the entire repair task is a transaction now. So it will, if it doesn't complete completely, it will fail, it will roll back. It's able to roll back. So yeah, incremental repair is pretty good.
I think we're going to keep moving. We do got some questions landing. One of the questions is about repairs, but we'll tackle that at the end. And there's another question about OLTP and OLAP systems. That will touch on some of this as well. So we see the questions. We'll get to you. Jumping on to the next topic. JBOD and LVM. I'm really happy, Romain, that you brought this one up because it's also one of my favorite topics. Having worked at the consultant at the last Spickle for 5 years, JBOD was one of those things we just wanted to throw out the window. So tell us a bit more about this.
Yeah, so the thing is that JBOD looks great on the paper when you first look at it, and I've had my share of trouble with it as well. So it looks great on the
just quickly describe, because it may not everyone or Cassandra operators may not understand what we mean.
Of course. JBOD, just a bunch of disks, is actually a simple way to set up your environment and say, I have 6 disks, and I'm going to create 6 directories, and in the data file directories of Cassandra YAML, you just set up those 6 disks to be used by your environment. Okay,
yeah.
And
so the Cassandra configuration, the YAML, is actually explicitly pointing to each separate disk.
Absolutely, each volume is separately notified, and so you can just, when you add a new disk, put the 7th pass in there. So on paper, it looks easy to administer, but the reality of it is quite more complex than that. First of all, JBOD acts as a kind of sub-vnode. So it will split your ranges into specific disks. So you end up multiplying that. There's another nasty effect I've realized over the course of the years when it comes to it is I mentioned the file descriptors. So the thing is that when you normally write, let's say, your data into your environment, you would flush one SS table. Except that when you introduce JBOD, I mentioned 6 disks. So if you have 6 disks at that point, you will flush 6 SS tables instead. And so you're multiplying the number of file descriptors in your environment by the number of JBOD disks you have. You will hit the no files limit of your kernel if you haven't implemented the best practices. The default kernel no files is generally at 100,000. Rest assured that if you write a lot in your environment, you will blow that number up at some point with a JBOD implementation. Because as I said, it acts as a direct multiplicator on the number of file descriptors you have in to connect to the SS tables. Because Cassandra will have a file descriptors open for every SS table in your data directory. So this is quite often there's the breaking point, cluster crash or a node crash because the no files limit has been hit. So that we'll push that as part of the best practices information. It's already documented in a fair few places, but something to keep in mind.
It is quite tricky. I'm going to ask you to keep moving.
Yeah, absolutely.
So why LVM and how do we do it?
So LVM, so logical volume management, is one of the Linux solution, which allows you to bundle your disks together. So you just create one partition which actually spreads across several disks. The con of it is just that you lose a disk, you lose your LVM. But in the reality of it, while it looks bad, JBOD gives you that false sense of I still have my data, but bringing a disk back in after you lost a disk in JBOD is a bit painful to deal with. You need to run a round of repair. Quite frankly, there's a replication factor in Cassandra for high availability failover. If you lose a disk, you lose the node, it's not a problem. You get a new disk, you rebuild an LVM, you rebootstrap the node in the cluster.
I think that's a really good point. I think like it's a typical, when we say you just use LVM, it makes life simple. People go, oh, but like I'm not setting up RAID redundancy in the LVM, and if I lose a disk, I lose that whole thing. And I think that JBOD's a better solution. And the conversation always comes back to, but Cassandra was designed for this. You've got distributed replicas. It's actually, life is much easier with just one whole entity going down and being able to replace it.
And the balancing act in JBOD is sometimes extremely painful. You can end up with an imbalance of the disks, and fixing that is sometimes quite tricky. Even the tool which is used for that, there's the node to relocate SS tables, doesn't always yield the results you want. So I would, it looks nice on paper, but the reality is an LVM is better. And if you want to keep the performance, that's where we recommend to use a striped LVM, which means your volume will actually split in small chunks across the different disks. So if you have 6 disks, you will have the performance of the disk multiplied by 6 when you're actually writing into the disks, as opposed to a linear one, which fills the first disk and then the second and then the third.
Yeah, and that can be incredibly important if you are running dense nodes. So good advice. I love that we included this slide. Thank you. Next up, major upgrades. So this is a slide that I'm going to talk to, but we've all done our time around this. The best bugs that we hit halfway through upgrades or post upgrades that haven't been done well. The first thing that I want to speak to is what are the upgrade paths that we want you to do and that we support. So when you're doing an upgrade, always first upgrade to the latest patch version on that major version that you're on. So if you're on 3.11, upgrade to the latest 3.11 first. This is because, and hopefully it's obvious. It's because with some of the bugs that we find, we can only fix those bugs in the source version, like in the version that you're upgrading from. It doesn't happen too often, but it happens infrequently. So that this advice is a wise one. Otherwise, since Cassandra 4, the Cassandra community has been more clear in that for online upgrades, where you're doing a rolling upgrade of each node while maintaining full availability and online, your services online, we recommend that you only upgrade between adjacent major releases. So what we mean by that is like adjacent major versions. So you can upgrade from any 3 version to any 4 version, but you can't upgrade from 3 to 5 and skip 4. For offline, we're getting better that you can upgrade SS tables from any version. This is particularly important if you start to think about backups. You want to pull out your backups, and they may be quite old, and you still need to read them. So we're at the SS table format level, we're trying to maintain compatibility. But when it comes to online upgrades, there's just too much to test and worry about, and the community only has so many resources to work with. So this constraint makes life easier and safer for everybody. A little text on this slide. The summary of it is there really is a lot of homework you've got to do with major upgrades. There are prerequisites that you should do. There's preparation steps that you should do, and the actual actions, sequence of actions that you should take are all super important. Reach out to support and get help. Don't underestimate any of this stuff. You want a smooth experience. Okay, jumping on. System changes. So, Romain, you brought this up.
Well, so I think, I think one of the important point here, as part of the discussion we had preparing this session, is to mention that it's important to know your data model. So it's just like nothing can replace that. I regularly get caught by request types that I didn't think existed. Mentioning, for example, a case I had quite a long time ago, but secondary index based on a Boolean value. And so you need to know your data model, because in that case, what happened is that a secondary index with a Boolean value means that if you have 5 million rows and they're spread evenly, your cardinality of 2, because your Boolean is 0 or 1, will mean you will bring 2.5 million documents, whether you're querying the 0 or the 1. So those are important consideration. You need to know what you have and how you're actually querying it, and have some idea of how it's going to make the computer behave as a result. So it's I regularly have challenges around that front because this is something that Cassandra will not necessarily show you.
So. Yeah, and you know, it's databases depend a lot on the underlying system.
Mm-hmm.
And especially like a lot of the Linux distributions, their default setup is not suitable for Cassandra technology. And so a lot of people come in and they're just going to start running, and there's some baseline advice that we have to offer. It's recommended, check it out. But also I think one of the other things is that once the penny drops on that front, and then they start investigating and learning all of the Linux and the underlying configuration changes that they can make, they jump in and they change everything at once.
That's what you mentioned here in the bullet point about doing the changes sequentially. It's just like one step at a time is generally a better approach.
One at a time.
I'll make an exception to the best practices, which are generally a good rule of thumb to get your environment going. Setting, assuring you that you have your reader heads correctly set, that the various kernel parameters I mentioned, no files earlier, which is one that you can hit, and when it hits you, the problem is that the kernel will just stop your process, so you end up with a node down. So some of the best practices really should be in place as a general rule.
Absolutely, and those things, what I've seen all too often is that they'll hit multiple nodes in a surprisingly similar point in time. They like all of a sudden the cluster is just falling over node after node after node. That's the last thing you want. And because Cassandra is set up properly, it's incredibly resilient. It's supposed to be an extremely resilient system that just keeps on working no matter what happens. This is one of the gotchas on that front. I'm really happy that you mentioned read ahead. I think read ahead and the GC tuning are your two low-hanging fruits to get huge improvements on systems. So thank you for that. We are really pushing for time. So I'm gonna jump over the tooling and the operational stuff. I'm going to jump. There is a call to action for this page, which I think is useful. There's documentation on the Cassandra website that's really rich, and it's recently new. Go check that out. It goes through a lot of the tools that we've mentioned here, and how to use them and when to use them. There was an item here, Romain, that it's really important for us to talk about. The new Mac. Tell us about it.
So yeah, I'll try to go quickly because I realize we're short on time here. Data stacks and Cassandra have some metric toolings available, but it's quite a bit. Let's put it that way. It's the jungle out there when it comes to all the different tools available. The Cassandra exporter, and we have designed ourselves MCAC, and we have the DSE metrics collector for data stacks, and all of those have their pros and cons. And we know that there's been some issues with notably MCAC and the DSE metrics collector, and there's genuine design flaws in them, which means they're really hard to fix. We've worked with our development team and with one of our colleagues in support, and he came up with a full documentation on how to use MAAC on premise. The idea being MAAC is actually part of the Cassandra operator offering. So if I take it, people have heard of Cassandra, which is one of the DataStax open source solution to deploy your environment on Kubernetes, and it has its own metric system, which is different from the previous ones I mentioned. But it's limited to Kubernetes. And what we've done is extract all the information and extract the agent from the existing Kubernetes environment, extract the graph data, which is originally provided in the code of Cassandra operator. And we have created a knowledge base article, which will allow you to use MAAC for on-prem deployment. Now, at this time, the KB is designed toward DSE. But the idea is that this is valid as well for Cassandra 4, Cassandra 4.1, and Cassandra 5. Because I mentioned MCAC earlier, MCAC doesn't go further than Cassandra 4.0, I believe. We have a 4.1 alpha, which was released, but never passed the alpha level. So I think it's a good takeaway as part of this discussion for people to be aware that we have been working on making this available even outside of Cassandra operator. And we have our first release, which came out literally 2 hours ago for the article.
Yeah. Nice one. So everyone who's struggling with enabling all your metrics monitoring on your Cassandra clusters, And if anyone who's using MCAC, pay attention to this. It's coming out. Thank you, Peter, for writing that blog post. And I'm going to thank Michael Berman, who I think is one of the engineers who did a lot of this work, which has been asked for a lot of people. Okay, I'm going to jump forward. I'm going to run quickly over a minute or two to get to the questions that we have. So having just a quick look at Cassandra 5, what have we got coming? The headliner has to be the Accord transactions. This is going to make Cassandra an ACID compliant system. In fact, because it implements strictly serializable isolation, it makes it the most ACID compliant database out there, on par with Spanner. This is big stuff, but probably more interesting to most people is what you can actually do with it. On this slide, there's an example syntax of the begin transaction, and how you can grab variables and then write a condition and then do something in that condition. This means one of the big wins with this will be you can now do referential integrity in your data model. This will be huge. It's about to get merged to trunk. Okay, so the next section, I'm going to jump to one key slide. We all know Gen AI is massive at the moment, and DataStax is pumping out products around Gen AI and RAG and vector search, because we're seeing such huge adoption around this, and the potential of what you can solve is everywhere, and it's brand new what you can do. The one place where this really touches on Cassandra is the vector search. Cassandra is a database which, we're seeing this brand new traffic shape and load land on the transactional database. So it's perfectly positioned for this, being that scalable database that can just take anything and stay super fast. On top of that, we have the vector search. The vector search has been implemented on top of the SAI indexes in Cassandra and allows you to do vector search through the order by clause. And you can do like global vector search in a table. You can do it within a partition, and you can also do hybrid against other indexes. So it's a very powerful feature. It's built on top of the JVector library, which is best in class. If you have a look at the version 3 of that JVector library, and how it's implemented disk and a number of other industry-leading solutions, it's blowing all the competitors and other open source solutions out of the water. I mentioned all the products that we're pumping out. So DataStax has this AI pass solution. So there's heaps here. Jump in. People talking in your company, you've got colleagues talking about Gen AI, mention this to them. There's in every hype cycle, there's so much noise. It's a little bit hard to kind of grab hold of what's real, what's happening. This is one of those things, and it's a really good opener. So this is something you can just kind of show, hey, look, here's a whole list of things for you to go check out and see if they match what you're currently exploring to do. Okay, let's get to the questions.
Yeah, we've got a couple of questions.
Yeah, there was a question in the chat as well, which we can jump back to. The first question,
I think there are.
on it.
I think the question in the chat was then put in the Q&A as well, because I think that's the same one from Ayodele.
Yeah.
Ayodele. Okay.
So, yeah, Ayodele is asking about changing parameters in YAML file for to switch between OLTP and OLAP. Now, Cassandra is not.
Should we each give 10 seconds on this one? What would be your highlight?
Yep. You can do analytics work using other tools like Spark or other tools outside of Cassandra, but Cassandra itself is an OLTP type of small and short operations, not really analytics operations. So this is my 10 seconds. Yeah, go ahead.
That's right. That's perfect. And it was a good introduction, Romain.
I'll give a try to it. I'd say depending on the number of, so it's all about the sizing of your box. You can potentially increase the concurrent reads and concurrent writes, but you also have to make sure you monitor your environment accordingly. Going back to what we mentioned originally, best practices should be in place. Read ahead is something on any Red Hat flavor that will bite you when you're so. Yeah, it also depends on what type of workload you have, reads, writes. So if you have a write-oriented workflow, use LCS. Use STCS. If you have a read-oriented workflow, use LCS. So 10:1 ratio for LCS. That's my 10 seconds version. But also check CPU and check the IO stat on your systems when you start doing this. So use NoSQL Bench, DSBulk, or some other tools to generate some stress on the environment.
See how it behaves. Yeah.
It's a good question because it has a whole lot of challenges. I mean, you're going from transaction database to analytics database. You're going from tuning for latency and removing long tails in the latency. You're going from probably a CP system to an AP system, and in analytics, you often don't care. You can just restart a job if it crashes. It still completes within a certain window. So you care more about throughput than you do latency, and so you do end up with quite different YAML files and quite different read ahead settings. And it goes all the way down the stack. And so we often see people creating a separate Cassandra data center and having their clients do the analytics workload of that second data center, where it can create as much instability as it wants, and everything has been tuned for throughput rather than low latency. So that's my takeaway. As far as individual YAML settings go, there's too many to touch on to give you a good answer, Adela. You can ask us that offline if you like. We'd be happy to help. Next question. In Cassandra 4, are both the unrepaired and repaired tables looked at for compaction, or is only repaired tables compacted? Francesco, do you want to answer that one?
Yeah, well, so if we're talking about manual compaction, all SS tables will be compacted. That depends on the compaction strategy. That's not driven by repair. So if you're talking about anti-compaction in incremental repair, then again, all SS tables will be anti-compacted, because it could happen that SS tables can mix, become mixed with repaired and unrepaired table.
So I would assume the question here is just about our normal compactions, not the anti-compaction.
So all SS tables will be.
Yeah, and you're right, and I think we've spoken before that there's now two different sets of SS tables. There's unrepaired and there's repaired, and the compaction now kind of splits those sets separately. So it will only compact the unrepaired SS tables together, and it will only compact the repaired SS tables together. So it does both, but it has to do them separately.
Yeah, I'm with Mick on that one. There's two streams of compaction occurring separately.
Yes, definitely. Yeah.
So the answer is, go ahead. Sorry, Francesco.
No, please go ahead.
So are they compacted? The answer is repaired is compacted and unrepaired is compacted, but separately. And it can bring its share of surprises as well. So we had a recent event where someone tried a major compaction on their environment, and they were expecting to shave a lot of data with it, and it didn't happen. And the reason was that because they had a repaired table, which dated back from 2022, and that couldn't compact with the unrepaired table. And there were some tombstones in the repaired table blocking the deletion of tombstones. So
this happens a lot with time window compaction strategy as well.
Mm-hmm.
And I think it's probably a really great answer for this question, because if you are seeing something that indicates this is not happening, there are reasons for that, and it's worth investigating.
Isn't that what we call shadow tombstones?
Yes, and there's a setting, like for time window compaction strategy, there's a setting called unsafe, aggressive. Yeah. I think I was partly responsible for that naming. Let's make it as scary as possible. But if the data model is right, it's a very effective, option to turn on. But you do need to turn it on both in the YAML and in the system property.
Yes, repairing tables with TWCS or LCS is not necessarily a great thing. I mean, the tables with it could mix up the time series and the time windows of the SS table. So
it's still
that's one effect.
I'm not sure what the challenge is with the LCS part, but I do agree. We know TWCS. TWCS is definitely something that is challenging to repair. I agree with that.
Yeah. And this problem can happen, like the example you gave, can happen elsewhere too. Where over time we're starting to lose some people. Thank you for everyone who's hung around to the end. Thank you, Romain and Francesco, for doing this together. It's been a pleasure. And as I said before, I'm the one who brought Christmas to the group, as you can see in my background. So I hope you all have a white Christmas and a good holiday season.
Thanks, Mick and Francesco, and everyone for being there.
Bye. Thank you, everyone.